And welcome to this video on fitting a line to data. Please like and subscribe if you find this video helpful and drop a comment to let me know what you think. So what we're going to look at in this video is the bigger picture. Sometimes in math class, we spend a lot of time looking at these abstract concepts. Okay, we look at these abstract ideas. We look at these points in a plane. So we draw an x-axis and a y-axis and we plot these points. And then we look at the relationships between those points, etc. and so forth. But what do those points mean? Why is it valuable to have a visual picture of those points? In other words, what's the bigger picture to what we're doing and why we spend so much time doing it? Well, math becomes interesting when we take it outside of math class and see the applications. And to some extent, that is my personal opinion, and we'll have more of my personal opinion in a future slide. Now, we may not be the one to do the application, but it can help to know that it is applicable. Anything that you're studying in middle school, high school, you are not going to use a lot of the very specific knowledge that you cover. Whether it's a history class, math class, science class, most people don't go on and become biologists. But having the background knowledge, first of all, opens up opportunities for you, but it also stretches us to look at the broader world of knowledge. So you might not ultimately end up being the one who does the application. Maybe you're not going to go on and do algebra in your future career. Now, maybe you will. We often don't know that at the time we're taking Algebra 1, but it might help you to know that it is applicable, that someone out there does use this information. Maybe that someone will be you, but certainly you benefit from the fact that other people are able to do it. It is a worthwhile thing to study. So in math class, our points are always perfectly straight. We know that the definition of a line, or one of the key concepts when it comes to talking about a line, is that, and then I don't put the line on the points. My hand is still bandaged at the moment. I have a sprained thumb, so it's a little bit hard for me to write. But in math class, when we're talking about lines, we're talking about a graph or a relationship between points where the slope is the same everywhere. So whether you are taking the slope at the bottom of the line, or whether you're taking it at the top of the line, you're taking it up here or here or here, that slope is always the same. And we know if we're talking about lines, we're talking about things that are perfectly straight. In real life, and I do put real life in quotation marks there because I don't want to build off this idea that math class isn't real life. Certainly there is a place for the abstract, for the idea. But when we take it outside of that, points are messy. They may approximate a line, but they won't make a perfect line due to imperfections in the tools that we use, imperfections in the environment, or just straight up user error. Like sometimes it's our fault. We don't read the ruler correctly, or our hand shakes a little bit. Maybe the scale that we're using isn't calibrated exactly right. We need our math to be able to transfer outside of math class and into this like real world. If it just stays abstract, for some people it will still be interesting, but not useful. And for a lot of us, it does come down to like, how is this useful? Again, maybe you won't be the one to use it, but it is nice to know that it is useful. So the way that we try to like work on that transfer skill is with application problems. And I almost put in my slide word problems, like that is word problems, but word problems aren't necessarily always application problems. So you could see word problems that are along the lines of name two numbers whose product is 10 and whose sum is 7. Well, that's a word problem, but it's not applying the math to anything. So when I say application problems, I specifically mean like things that model real world situations and real world data. We can do that with activities. Now, I know I do like doing activities in my class. In my math classes, I often don't have time to do activities. We have so much content we have to cover, and you take a day and you play with ping pong balls for that day, It can get chaotic, and maybe the point gets lost, and it's like, oh, well, we got to move on to the next thing. Sometimes we have discussions. Sometimes we might have those classroom discussions where we talk about applications or ways that we've seen math apply. And if your teacher does that, participate in those discussions. Offer your ideas, even if you think your ideas are kind of silly, or even if you're like, well, I don't know how it's applied. Can you give us an example? You always want to keep it respectful, but engage in those discussions, and that can often lead to activities if you'd like to do them. So in this lesson, we're going to revisit a class activity my engineering students did. And if you've been watching these videos, I do reference this activity in an earlier video. I think I pulled a different student's data. I think I had several students, and hopefully I did, but if I didn't, fine. So what students were exploring was the relationship between the force applied to a spring and how much the spring stretched. And if you picture this, like if you have a spring and you pull on the spring is going to stretch out. Okay. And again, I'm sorry, like I am writing with a spring thumb. So my dominant hand, it's not fun. So what they did was they used a spring scale to apply the force. So they had a spring, and then they had attached to the spring, it was like a little hook, okay? And it was attached to this thing called a spring scale, and that was graduated. And then they held or anchored the end of the spring down, and then they pulled on the spring scale. So this would be like a 0 up here, 0 newtons. Okay, newtons is a unit of force. It tells you like how hard you're pushing or you're pulling. And then they would apply a force, the spring would stretch, and we'll put a little hook there. Okay, and here's our spring scale, and maybe that was 0 newtons, and then they applied a force, and now it said 6 newtons, and like you could see the gauge in the spring scale move, and it says 6 newtons. And then they took a ruler and they would measure how much the spring had stretched. And then they had to do that for 0 newtons, which would be no stretch, so you're not applying any force, 2, 4, 6, 8, and 10 newtons. I had some groups that did not go all the way up to 10 newtons because by the time they were pulling that hard on the spring, they were actually going to break the spring. So the spring was going to stretch and not rebound. So we didn't want to do that. And so that's what the activity was. And then they had to set up their data table, and they had the force in newtons, and they might have 0, 2, 4, and so forth. And then they had the displacement of the spring. And the one we're going to look at, the student used centimeters, but I did let them use whatever they wanted for the units. And let's take a look at some student work. So I did take the student's name off of this. So this is her work. And what I'm going to do on this slide is just talk you through her work. So what did she do? And I'm going to try to refrain from commenting on what I think is good or not good about her work, or where I think she could be better. So over here, you see her data table. And she does have the data table. Everything is clearly labeled. So she has force in newtons, and she was able to apply a force of up to 10 newtons, displacement of the spring in centimeters, and there's her data in centimeters. And then they had to graph it. And so you see she has force on the x-axis and displacement, and again, the units on the y-axis. She counts by 1 newton each time, and she counts up by half of a centimeter each time on her y-axis. And then we could check and see if she plots her points correctly. So 0, 0 would be the origin. 2.6, she's got it sitting just above the 0.5. 4, 2. Okay, that's what we call a lattice point, although she ends up not using it. 6 and 3.5. So there's another lattice point right there. 8 and 5.3. So you got 5 and then 5.5, and her 5.3 is just in between. And then 10 and 6.8. And again, we have 6.5 and 7, and she puts it a little bit closer to the 7. So it's in the middle, maybe nudged up a little bit closer to the 7. Okay, so we have those data points, and you can tell looking at those data points that is definitely a linear relationship, but the points aren't making a perfect line. And so her task was to do what's called a line of best fit. And a line of best fit is the line that comes as close to as many data points as possible. So the line of best fit. Okay, it is a line, so it has to be a line, so you can't do like connecting the dots like that. Okay, that would not be a line. So it's a line that comes as close as possible to as many points as possible. And it might go through all the points. Like if your points actually did end up being perfect, then your line of best fit would go through all of them. But your line of best fit might not go through any of your points. And she made hers go through the origin, 0, 0. So we'll talk about that a little bit more in a moment. But if you look closely at her points, her line of best fit actually doesn't go through any of them. So the line of best fit is sitting above these points right here, and it's sitting below these points. And like her goal was, okay, let me put a line on here that is going to approximate where like I think these points really should be in real life. Now, the task was to write the equation of a line. So at this point, we've covered enough that we know that we should be able to write the equation for a line. So what she did was she looked at her line. Okay, not at her data points anymore, because her data points may not be on the line. And she chooses 2 lattice points. So she chooses the point 4, 2.5. Now notice her actual data point was 4, 2, but her line right here goes through the point 4, 2.5. And then she chooses this point here, which is 5.5, 3.5. So halfway between the 5 and the 6, and up here at the 3.5. So she chooses 2 points that are on her line, the actual line she drew. They're not her data points. Now here she's got her formula for slope. So y2 minus y1 over x2 minus x1. And she actually labels the work there is equal to m. She plugs in her numbers. So 3.5 minus 2.5, difference in the y's, over the difference in the x's, 5.5 minus 4, and she ends up with 1 over 1.5. So she says her slope is 1 over 1.5, has a little arrow. So there's her slope-intercept form. She plugs in 1 over 1.5 for the m, and she pulls the 0 from her graph and her data table. So she had drawn her line to go through the origin, so her y-intercept was 0, and she did not bother writing the plus 0. She could have plus 0 there. And then right here, she just subs out the variables. So instead of y and x, she says, well, what's on my y-axis? Well, that's displacement. So we'll say displacement is equal to 1 over 1.5. What's on her x-axis? That is force. And so she uses an F. So now she's got this equation, displacement is equal to 1 over 1.5 F. And then the final part was make a prediction. How far do you think your spring would stretch if you applied 15 newtons? So if she were to go out 11, 12, 13, 14, 15, where would that be? Okay, we're going like way up here somewhere. Where would that be? And that's where the math comes in useful. It's predictive. The spring scales that they were using only went up to 10 newtons. So this was not something that they could actually measure. They have to make a prediction for like how far. And this would be really important. We talked about this in the engineering class. If you're choosing a spring for a design, you need to know how that spring is going to behave. Is it going to stretch too much? Not enough? Will it break if we stretch it that far? And so she took her mathematical model that she created here. She plugs in 15 for the force, and then carries out that calculation and gets 10 centimeters, and she like boxes that in and says displacement will be 10 centimeters at 15 newtons applied. And so that is the complete set of work, from gathering the data, looking at the graph, doing what's called, again, that line of best fit, and then finding the mathematical model for that. And what she did was she was employing the skill, write the equation of a line, given 2 points. All right, now I want you to pause the video and I want you to think on this. What did this student do well? And if you need to rewind the video and just look at the work again, like, go ahead and do that. Like, what did she do well? Because there is a lot that is very, very well done in that work. Where do you think she could have improved? And I think there are some places where she could have improved also. But what about you? Where do you think she could have improved on something? Like, maybe something was a little bit awkward or unclear or uncomfortable that we could have done something. And do you think the quality of the student's work demonstrates that she understands the concepts? And I really want you to reflect on that, because as students, sometimes there's a temptation to get really caught up in the grade and getting it done. And we forget that the point of doing the work is to emphasize like a learning goal or to demonstrate that you do understand certain concepts. So do you think the quality of this student's work demonstrates clearly that she understands the concepts? And ultimately, that's what a teacher needs to do when they are evaluating your work. All right. Now, graphing utilities will often do this for you. So graphing utilities would include like your battery of graphing calculators. I use Desmos for this, okay? And we can kind of talk about how that student did her work. So over here, you'll see that on Desmos, I entered in the data table, and I'm going to upload a video like showing you how to do this. So check out the channel to see if you can find that video. If I can, I'll link it in the description for this video, just like how would you go about doing that. So you enter in the data table, and notice the subscript here and where it says X1 and Y1. That subscript just means table 1. So if you had more than one table, you'd have like X2, Y2, X3, Y3, and so forth. So that little 1 just means this is our first table that we're working with. If you look over here, you'll see all of those points, and these are the same points that the student was using for her activity. And then to do the line of best fit, you use the Y1 and the X1, and that just tells the graphing utility, or Desmos in this case, please reference the data from the table, okay? Like, because you might have more than one table, so you use the X1 and the Y1. Instead of an equal sign, you use a tilde, okay? So this is what we call like the syntax, like how do you talk to your graphing utility. So use a tilde, and then you'll see the M and the B. And so what that statement is it's telling you, find me the equation of a line, okay, y equals mx plus b, but use the x1 and the y1 from the table, and then this part, the tilde, is like kind of the command. And then what you'll notice is it gives you a slope. So it gives the slope of 0.70, well, you guys can read it, and it gives you a y-intercept. And it also gives you some stats and residuals. So residuals you can talk about in like, that would be like a pre-calculus class. And these are statistics. And basically what those numbers are saying in a nutshell is how good does this line model the data? Like, does it look like it's a line? And notice a couple of things about the line, and it automatically graphs it. Like the student's line, these first 3 data points are below the line and the second 2 are above. What's different about it is this one does not go through the origin. So it's actually sitting below the origin, and you can see that the y-intercept that it gave was about like -0.5. So what I did on this line was I took the M and the B and I basically plugged them in with the 15, and we got a prediction of 11.2 centimeters. So that is lower than the student's. She got a prediction of 10 centimeters. This one is predicting something a little bit longer than that. Now, keep in mind, and I said we were going to come back to this, the student drew her line of best fit and she went through the origin. she said, I know that is true. If I do not apply any force, that the spring stretches 0 centimeters. And so she made sure she included that point. So what I did on this next slide was I omitted the plus B. Let's assume it does go through the origin. And that what that did was it forced the line to go through the origin. And you'll notice it's still above these 3 points and below these 2 points, okay? But now it's like tilted a little bit differently. It's got a more gradual slope. So the slope is 0.639 something because we kind of bumped it over to the left. And when I modeled that one, we got 9.586. So this model actually went a little bit lower than the student's model. So one of them was a little bit higher, this one was a little bit lower. And you can get a good idea for how like fitting of the lines works, picking the model for that, and then what you can use it for. So once you have your mathematical model, you can use that to predict future values. And you won't have to think too long to think, oh, we could do that with money and with, the space shuttle and all kinds of stuff. All right, there's no separate practice set on this video because this is a kind of hard thing. Like I would have to give you some data, and then if you're doing it at home, you're all going to come up with like different models. Like that student was part of a group and they had the same data and they would come up with different models even with the same data. But keep this lesson in mind the next time you're in science class and you're looking at graphs. Like and subscribe for more math content. Check out the videos linked below, and I will see you in the next video.